In this video, we're going to talk about the binomial distribution. And this is just going to kind of be a quick review. We'll kind of do half the problems that we didn't do in class. So first, let's remind ourselves that the requirements to use a binomial distribution are, first, that we have a fixed number of observations. We know in advance how many times we're going to do our experiment. The n observations are all independent, so the first one shouldn't affect the next one, etc. Each observation is classified as either success or failure, so something's either yes or no. You only have two options. And the probability of success P is the same for each observation. So with that in mind, let's go to the next page and we're going to practice identifying whether or not something is binomial. So number 4, we want to draw two cards from a standard 52 card deck without replacement. So again, this is the keyword here, without replacement, so we don't put them back. Let's consider drawing a heart a success. So when I go through these and I write down things like, okay, how many times are we doing something? We are going to do it 2 times. We're drawing 2 cards. And then we're specifically looking for, is it a yes or no, success or failure? So we're considering drawing a heart a success. So we are specifically looking here for heart or not heart. Okay, so that's good. That fits binomial. Okay, and then we want to check, is it independent? Does the first one affect the next one? So in this case, they are not independent because we drew without replacement. So the first card we get affects which card we get the next time. Or the probabilities change, because if I draw out a heart, then I have one less heart to choose from next time. Okay, so because it was not independent, it doesn't fit, so this one is not binomial. So it had a fixed number of n, it had success or failures, yes, but when we got to the independent clause, it failed that. Let's try our next one then. So we decide to roll a die until we get a 6. We let x be the number of times we have to roll a die. Okay. So in this case, do you know how many times you're doing the experiment? No. So we don't know n because we roll until we get a 6. We don't know how many times we're doing this. Okay, and so it is not binomial. This should be a little lowercase n to keep with all of our notation. Let's try the next one. We roll 2 dice and we let x be the sum of the values on the dice. So if you roll 2 dice, what are your possible values? You could get x could be like a 2 or a 3, all the way up to 12. Those are possible values. But does this sound like we just have 2 options of success or failure? So no, we not just 2 options, not just success or failure. And specifically, we aren't counting successes. Binomial always lets you count the successes. So this one again would be not binomial. Now let's suppose that we have an auditor that examines a sample of 150 records out of a total of 100,000 records that are available. One issue is whether or not each cell was correctly classified as subject to state sales tax or not. Suppose that 800 of the 100,000 cells are incorrectly classified. Is the count x of misclassified records in the sample a binomial random variable? So let's go through and see. Notice this did say without replacement. So that makes sense. Okay. Well, actually, it didn't say that. I'm saying that because if you're sampling records, you're not going to pull one out and then put it back because you don't want to sample the same one twice. So anytime you're sampling, you're always going to do it without replacement. Okay. So with that note, let's move on to saying, is it binomial? So first you say, okay, how many times am I doing it? We know we're taking a sample of 150, so n equals 150. Then you want to see, is there a success or failure? So in this case, it's accurate or incorrect. So that's correct. Good. Then you want to say, are they independent? Does one affect the next one? Okay. And no, these are not independent because it was without replacement. So the first one affects the second one, etc. And with that in mind, you could also say, does the probability stay constant? And no, the probability changes from first to second, etc. Because again, you're doing it without replacement. You're not putting back, so the probability changes. And so this one is not binomial. And so I say, okay, not binomial. Well, okay, now I guess I can't actually do anything with this. But it turns out that this is actually a situation where you could still use the binomial distribution, okay, because this is a special circumstance. So let's come over here and talk about the special circumstance. So turns out that for all practical purposes, we can use the binomial distribution. So again, for all practical purposes, we can use the binomial distribution here because the difference caused by the probability changing when we sample without replacement is so small that we really just don't care. Now, as a rule of thumb, we can do this when we have a large population. So if our population is at least 20 times larger than our sample, you can go ahead and still use the binomial distribution even if you're sampling without replacement. To see this, let's look at a couple probabilities. So let's look at probability of first two being incorrect. And let's do the first one here. Let's try it with replacement. And then over here, let's try it without replacement. Now again, practically, you never do it with replacement, but let's just see what that probability would be. Okay, so if we want our first two to be incorrect, notice there are 800 out of the 100,000 that are incorrect. Okay. So if I want the first one to be incorrect, I would have 800 out of 100,000. And then I want another incorrect one, but if I'm doing it with replacement, I put my first one back, so I still have 800 out of 100,000. This is 6.4 times 10 to the negative fifth power. Now let's try it without replacement. So the first time I would have 800 out of 100,000. And then the next time I've already used one of the incorrects and I didn't put it back now, so now I only have 799 incorrects out of 99,999. Now, do you think that these two numbers are going to be much different? No, I probably don't care if it's 800 or 799 out of 100,000 or 999,999. Let's see what that would actually be. It's going to be 6.392 times 10 to the negative 5. So it's going to be almost exactly the same. The difference in the probabilities are so small that we really just don't care practically. So you'll find if we want to take a sample without replacement, and as long as our population is really big, we can still use the binomial distribution. So then our next section is probabilities. So we're going to do that first page in class. So let's look at our next example. So Mark has an overall free throw percentage of 70%. Mark attempts six free throw shots. Assume independence, so let's assume if he makes one, it doesn't affect whether or not he makes the next one. And we'll let x be the number of free throws he makes. So first, can we use the binomial distribution here? Let's see, do you know how many times you're doing it in advance? Yes, he's doing it 6 times. Okay, so that's good. Is it a success or failure? Well, he's either going to hit or miss. Okay, so that's a kind of yes or no thing. It told us that we can assume independence. So that's good. And it said that the probability of making each shot will say 0.7. Each one's independent. It shouldn't be changing, okay, because they said he has a 70% chance. Check. And so this one is binomial. So now what is the probability that he will make 2 shots? So to do this, we need to go back and look at our probability formula. So probability formula, the probability that x is some specific number is going to be n choose x, p to the x, 1 minus p to the n minus x. So let's write that down. probability that x equals some specific value is going to be n choose x, p to the x, 1 minus p, n minus x. So this n choose x, that's how many ways you can get that specific thing. This p to the x is, we need the probability of getting x successes, so you need the probability of make it, and then you need this many failures. And so you do 1 minus p, probability of failure, and n minus x failures. So for 2 shots, this specifically will be probability that x equals 2 is we had 6 chances and we need to choose 2 of them to be hits. We have a 0.7 chance of making a hit, and I need to make the hit 2 times. And then 1 minus 0.7 is the probability of missing, and I need to miss 6 minus 2 times, or 4 times. And this should be 0.0595. See, next, what if we want the probability that he makes less than 2 shots? So less than, probability that x is less than 2. Notice less than 2 means we're not going to include the 2. So less than 2 shots would be the probability that x equals 0 plus the probability that x equals 1. So you have to find the probability for each number that's less than 2. So we'll just go ahead and plug these numbers back into our formula. So first we'll have 6 choose 0 times 0.7 to the power of 0, because I need 0 of them, and 1 minus 0.7 to the 6 minus 0. Plus, and then I'll do a 6 choose 1 for probability x equals 1, 0.7 to the 1, and 1 minus 0.7 to the 6 minus 1. Okay, so you can check your calculator work. This should be 0.000729 and 0.010206, which should give me 0.010935. And a lot of you probably have calculators that can do this for you, and that's okay, as long as you know that you should set it up as a binomial probability. That's fine if you use your calculator. Okay, and probability that he will make 5 or more shots. So now we're looking for the probability that x is greater than or equal to 5. So 5 or more. So in our case, that would be probability that x equals 5, or the probability that x equals 6, or we will do an add, because we're talking about an or, so he needs to make 5 or 6 shots. So let's just plug those numbers in. So we'll do a 6 choose 5, 0.7 to the 5, 1 minus 0.7 to the 6 minus 5. And 6 choose 6, 0.7 to the 6, 1 minus 0.7 to the 6 minus 6. And this should be 0.420175. And finally, probability that he'll make at least 1 shot. So we're looking for the probability that x is greater than or equal to 1. So you could do this. Greater than or equal to 1 means 1, or 2, or 3, or 4, or 5, or 6. So you could find each of those probabilities one at a time, but you probably don't want to. So we'll use the complement rule. The probability of at least 1 is always going to be 1 minus the probability of none. So 1 minus the probability that x equals 0. And we actually found that up above. Right here, probability that x equals 0. So 1 minus 0.000729. So 0.999271. Okay, and then in class, we're going to learn how to find the mean and standard deviation. We're going to actually go through a proof. So if you have a binomial, n and p, let's find the mean and standard deviation. So I'm just going to show you here what they are, because you should go to class before you see this movie. The expected value is n times p, and the variance is np times 1 minus p. So let's try example 96 here in our video. So in a test for ESP, a subject is shown the back of a card. The card can be a star, circle, wave, or square. The subject is supposed to guess the name of the shape on the card. Each subject will look at 20 cards and assume each subject is randomly guessing. So first, would it be binomial? Yes, so each subject looks at 20 cards, so you know that n is going to be 20. And we're assuming that they're guessing, and so we'd say you're either correct or not. Okay, it should be independent. Each one shouldn't affect the next. And the probability of getting one correct would be 0.25 because there are 1, 2, 3, 4 shapes. So the probability is 0.25. So this is binomial. So what is the mean number of correct guesses, or the expected value? So the expected value is n times p, so in our case it's going to be 20 times 0.25, which equals 5. And that makes sense. If you're just randomly guessing and you have a 1/4 chance of getting it right, you do it 20 times, a fourth of 20 is 5. You'd expect to be right about 5 times. We expect them to be right about 5 out of 20 times. Now it's not going to be exactly 5, but that's what we expect. And to find standard deviation is the square root of variance. So it's the square root of np times 1 minus p. So the square root of 20 times 0.25 times 1 minus 0.25, which is the square root of 3.75, so 1.936.